Hi, I'm going to continue Virtual Memory System, section 5.2. Main motivation is protection and relocation of the code at runtime. I'm going to discuss those two issues later. Mentioned earlier that virtual memory system, typically the hard disk drive, it takes 1 million cycles, and memory access takes just 100 cycles. So in terms of a ratio, it is a 10 thousandths. So you really want to reduce the memory miss as much as possible. Memory miss in this case is called a page fault because memory and virtual memory is divided into pages. Gave you an example with the virtual memory system on the left hand side and the memory system in the middle and the cache on the right hand side. So two pages are actually mapped into the physical memory, and the 3 blocks in the memory are mapped into the cache at this point. There are 8 pages in the virtual memory. There are 4 pages in the main memory, and the mapping table is maintained in the data structure called the page table in the middle top. So as an example, we covered the virtual address 7D6. So 7D6, as you can see, 7D6 in the virtual memory space is at the bottom. I indicate with a red dot, and it is actually mapped into the physical page number 3. And then fortunately that particular memory block is already copied into the cache. So this is going to be a page hit and also the cache hit. Of course, that will be validated using the page table and the cache tag value. In other words, the virtual address 7D6, virtual page number 7, page offset D6. So using the page table, virtual page number 7 is translated into physical page number PPN 3, and page offset stays the same. For the cache access, they decompose into 3 tag value, block index D, block offset 6. So the tag value 3 is the same as the tag value from the corresponding cache block. So it is a cache hit. So let us say virtual address 133 I indicate as a red dot in the left hand side, and it is already in the map into the physical memory. So definitely it is a page table hit. On the other hand, the corresponding memory block is not in the cache, so it is a page table hit, but cache miss. So when the CPU is given the memory address, again, it is decomposed into VPN1, page offset 33, and translate using page table to PPN1. Page offset stays the same, and for the cache access, tag is 1, block index 3, block offset 3. So the tag value from the memory address is not the same as the tag value from the cache. So it is not a match. So it is a page table hit, but unfortunately cache miss. Last example, 309. I indicate 309 in virtual memory space. Unfortunately, it is not mapped into the physical memory. So definitely this is a page miss. In order to emphasize that, this is called the page fault. So summarize is that the first case, page table hit, cache hit. Second case, page table hit, but cache miss. You need to consume 100 cycles to access the main memory. Last case is a page table miss, page fault. You need to access the hard disk drive to access that particular page from the hard disk drive, consuming 1 million cycles. So the idea behind the virtual address access is address translation process. So from the virtual address to the physical address. So, given the virtual address on the right hand side, 32-bit virtual address, page offset stays the same, but virtual page number, PPN, is translated into the PPN, physical page number, using page table. So this process is called the address translation. So as an example, the 32-bit architecture, 32-bit virtual page number, 32-bit virtual address, and the page offset is a 12-bit. You can easily see that based on page offset 12-bit, you can compute that the page size is a 4K byte. On the left-hand side, the virtual page number is a 20-bit, which means that you need 2/20 page table entries or 1 million entries in the page table. So considering the page table size, let us say each entry is 4 byte, and altogether the page table size is over 4 megabyte, because there are 1 million entries, and each entry is a 4 byte. So just giving you a more physical, sense of what is going on. The CPU on the left-hand side, and there is connected to the memory and disk controller using the bus. And the CPU, in fact, is producing the virtual address. So, if you think about the load word instruction and store word instruction, actually they are producing the virtual address instead of physical memory address. And then memory management unit is translating, it is handling with the page table, all the corresponding logic, and producing the page physical address. And of course, the cache is probably after the memory management unit and the bus. And part of the cache is inside the CPU, and part of the cache is outside of CPU. Level 1 cache, level 2 cache. And so on. So I noted one problem on the right hand side of the slide. So the problem is that page table is in memory. So which means that in order to translate, memory management unit is translating virtual address to physical address. But at that time, it already go to the bus to access the memory, because page table is already in the is in the memory. So although the best case scenario in the previous three cases, the page table hit and cache hit, but you still need to consume 100 cycles because page table is inside the main memory. So that is basically a main issue we are going to discuss in the next slide. So the best case, you're still consuming 100 cycles. That's not desirable at all. So we keep a small subset of page table inside as a cache inside the CPU, and that is called the translation leukocyte buffer. So this is a small subset of page table. So it is inside the CPU. Accessing TLB is just one cycle. So if you consider the best case scenario, you don't have to consume 100 cycles, because TLB is inside the cache, inside the CPU, that consumes just one cycle. So translation leukocyte buffer is just, it's just the same idea of the cache, regular cache. Most frequently accessed, page table entry is copied into the TLB. So TLB is a hardware cache for page table access. Translation leukocyte buffer. And just giving you a more comprehensive example, this is one of the real system. We'll cover the cache first. The block size is, since there are 2 bits for the block byte offset, so 2/2 is a 4 byte is a block size, and tag size, as you can see on the left hand side in the middle, that's a 16, which means that and then number of entries in the cache is because the cache index is a 14-bit, so 2/14 is a 16K. So there are 16,000 blocks in the cache, And cache access method in this case is a direct mapped cache, because using the cache index, you indicate just the one single block, so that's a direct mapped cache. So let us look at the virtual memory system on the top. So what is the page size, what is the virtual memory space, physical memory space, number of entries in the TLB, and what is the TLB access method. So virtual memory space, virtual memory system, the page size is, because page offset is a 12-bit, so 2/12 is a 4K byte. So the page size is a 4K byte. Number of entries in the TLB is, you can visually, see that there are there are 8 entries in the TLB. The TLB access method is a fully associative cache. As you can see, the virtual page number from the memory address is compared to all the tag value in the TLB entries in the TLB. So it is a fully associative cache. So this looks a little bit complicated, but it is just the CPU is given a memory address. What is happening? Basically, it is a two-step process. The first of all, address translation. So virtual address is translating to the physical address, and the second step is using the physical address, you access the cache. So in the first the address translation process, you are translating using the TLB, and otherwise you're using page table. And if you're not able to find it in the page table, that's going to be page fault. So just an example with the Intel CPU, it is a 4-core architecture, and as you can see, there are 4 cores in the figure, and at the bottom there is a level 2 cache and level 3 cache. Level 1 cache is inside the core, so it is not shown in the picture. I shared this slide earlier. There's a level 1 cache is an I instruction cache. The data cache is separated, 32K each. And level 2 cache is a 256K, and level 3 is 8 megabyte cache, and that's we discussed earlier. And in the same architecture, the TLB is level 1 TLB and level 2 TLB. And level 1, they are using instruction data separately, and 128 entries and 64 entries. And level 2, there are 512 entries. Just the one thing I want to emphasize, the page table and virtual memory space is, every process must have a separate virtual memory space and separate page table. So just assuming we are running 2 processes in the system, let us say, first one is an Excel process, the other one is your program. You are actually running the two program at the same time, and the page table and the virtual memory space, is a map into the physical memory in a different manner. So I'm going to explain the relocation issue on the left-hand side. Let us say Excel program. You don't have any control over the physical memory, because physical memory, sometimes you have a lot of programs running at the same time. So you're not able to load your the Excel program, exactly on page number 3, for example. But on the physical, on the virtual memory side, you can do that, because this is your, Excel program is running, on its own. There is no other program here. On the right-hand side, the protection idea is that you're able to protect, one program from the other. For example, in this case, your program is not able to access XXX, which is physical address, page number 1. It belongs to the Excel process, but you're not able to, your program is not able to access this part because it is not mapped to your virtual memory space at all. Thank you.